All right, so once you pull up your last first thing we want to do is increment that number. So save it as 4, like change the 3 to a 4. So we'll go into project view. I'm gonna have to move this camera a little bit because I'm not gonna be able to do what I need to do. I'll type in this one. If that goes out, let me know. All right, so go up to project, do a save as, and then change the number on there. Like, so it'd be PLC, whatever class you're in, underscore, whatever lab you're doing, underscore your name. Go ahead and save it. So I'm gonna keep everything that we've done up till this point saved as 3, and then now we can change this over without, messing with our last lab. Y'all got that yet? Okay. Like, all right. So, I'll just talk about what we'll do today, while y'all get it up, and I'll check back in a second. All right. So let's look at our program blocks that we have. We have an analog scaling, we have a sequencer, and we have a VFD. Okay. I want to go back to the analog scaling because I want to make that a lot more powerful than it is, because we're going to use it a bunch. Like right now, I'm writing code for ESP32 to communicate with the PLC. And what that'll do is I'm making these little circuit boards that will plug in like the simulators. And then that ESP32 will provide us with practically anything that we could want. Like where we might not have a differential pressure transmitter on hand, or you might not at the house, like the ESP32 will mimic that. And, instead of having to spend $400 on a sensor, we can get cheap, like $10 sensors and communicate with the ESP32, which then communicates with the PLC. So to the PLC, it just looks like that sensor. But, well, all right, so if you buy an industrial, let's say I want to measure water, okay? Like that waveguide out there is like $1,000, and it's huge. Okay. Well, did y'all see the little laser sensor I had? Like, it's a distance sensor. It's called a time of flight sensor, and it's pretty resolute. But they're, I think, $10 a pop. The little ultrasonic sensors that I've got, they ping out a little frequency, and then they wait and listen for it back and divide that by 2, and you can tell how far something is because sound of, speed of sound. Well, it's really hard to get cheap industrial grade components, and they're usually really huge. All right. So my plan is, to have a system that you could take home that would fit in a little box like this big. And then, like anything I could think of, I could program that little microprocessor that's going to be on there to mimic that. Okay. So, like, let's say that we do have that waveguide. All right, you plug it in, it'd read that way. Or if instead of using the waveguide, I had y'all use a little laser sensor, the laser sensor doesn't talk in 4 to 20 milliamps. Okay, it talks in what's called I2C, which is a little serial communication protocol. Well, the PLC doesn't talk in that. So we'll use that little microprocessor to convert that into something the PLC can read. Cool. All right, so what we're going to do today is I'm about to prove that concept before I get these boards made. I'm sending some boards off to China to get made. I designed that'll plug in like a simulator will, and I'll show y'all it later. But like the only thing I want different, like I don't want people to have to code to talk to that ESP32. Like I want a function block that I can put out online. You pull that function block in, and that's one of the great things about function blocks is if you make a good one, you don't have to. You could save it and then use it in anything that you want. You know, not the same project that you're in. All right, so we're going to we're going to build some a function block that kind of does this analog scaling for us. Okay. All right. So analog in 0 to 27,648. All right, that's 0 to 10 volts, and then it's going to get converted into what's called a count. Okay. It's beyond the scope of here to explain what a count is, but like if I can put a timer on a counter and I could compare a voltage that I know to a voltage that I don't know, and I can just keep pushing up that voltage until it equals. Okay. And that's in general what we're talking about. Like it zooms up real quick and then it matches the voltage, and then boom, it knows what the voltage is. Okay. All right. So one of the things that y'all will do, like you won't have the circuit board for it, but at the end of this, like when you're in lab, I'll give you a ESP32 that'll be set up that me and the people in the class are going to put together to simulate some of this stuff. Okay. All right, so the ESP32 cannot output a 10 volt. It can only output 3.3 volts. Okay. So we're going to have to rescale everything, and we're going to lose, 6.7 volts worth of resolution, but that's not that big of an issue. Okay. So, do y'all have y'all's analog scaling function up? All right. So, the analog in, will be whatever we put in there. Now, this box right here, we're going to make a new one. Okay. And it's going to be called simulator. Okay. So add a new block. And what this does is it's like glue logic. It's going to make it so that I can output a 0 to 10 volts to that simulator, but it's not actually outputting a 0 to 10 volts. I put it into this box and it'll convert it to whatever I need it to be. Okay. Because 10 volts will fry that little microprocessor. Okay. So what we're going to do is we're going to make a function block, and let's name it ESP32 underscore simulator. All right. click OK. While that's going, I'm going to make sure my let me draw out the easy part of the circuit. Function block. All right, that's what the simulator looks like on schematic. All right, there's a lot to it, but it's going to be good. All right, so our two analog outputs the first one is going to go to the processor. Okay, both analog inputs are coming from the processor. So we're taking the two analog inputs and we're just reading a DAC, which is a digital to analog converter. Yeah. And then we're taking the first analog output of the PLC and putting it out back to the microprocessor. And then we're taking the second analog output and we're putting it out to the daughter board. So you'd be able to connect these modules up. Instead of wiring up to the PLC, you'll just plug in an Ethernet cable and plug in another Ethernet cable, and you've got this little board that you can put a bunch of stuff on. So the analog output 2 is going to go to that daughter board. It's just going to bypass that so that we can get 0 to 10 raw out. Okay, so let me draw that real quick so that we have it and we can reference it when we need to. All right. Is this up there? All right. So we've got our microprocessor. It's called an ESP32. And it can only handle 3.3 volts. Okay. We're dealing with the analog right now. This can deal with 0 to 10 volts. The two analog ends are going to both be connected to the analog outputs over here. Okay, the digital analog converters. Or actually that'd be an ADAC because it's an input analog to digital converter. Okay. Then we're going to take the output of the ESP32. Oh, I was right the first time. All right, so the two inputs of the PLC are coming from the outputs of the ESP32. Okay. And then the one output, or one AQ0, is going to the input of the 32, and AQ1 is going out to the daughter board so that we can use it in the real world. Okay. Now, the reason I put both of those analog inputs connected to the ESP32 is because I've got 4 potentiometers that are connected to that, and through code we can decide which one of those potentiometers is going out to each one of those analog inputs. Okay, so we lose 2 analog inputs, but we gain 4. Okay, it's not just those potentiometers that can be controlled by that. We could have like that laser sensor I'm talking about, we could have that converted into an analog output that will be sent there. So that is what we're going to do now. All right. So when I'm making a function block that I'm going to use a lot of, okay? Now, I don't want the person who's using this function block to screw up, okay? Like, so if they wire up a 0 to 10 volt signal to the analog out 1, we're going to fry that microprocessor, okay? So whenever they put this on there, they use this code block. All right, so now up until this point, if we needed somebody to be able to add something like in the analog scaling, we let them choose what output it went to, right? We're not going to do that on some of this, okay? Now, the more I think about it, I kind of want to, I'll probably make it so that it won't damage the, I could add, you know, a little drop down circuit, but we want to make sure that they're just putting out 3.3 volts. Okay. Even if I put the protection circuit on there, the output 10 is just wasted, you know, whatever, heat. Okay. So let's take a mystery box and put it down here. All right. Let's do a norm. Then another mystery box. And we're going to do a scale. And y'all are pretty confident in what the normalization and the scaling function do, right? Normalization just scales it to 0 to 1, and the scale takes that normalized signal or normalized value and converts it into another range, okay? All right, so we definitely need to make sure that our analog out one, or our first analog output, never gets over 3.3 volts. Okay? Cool. All right, so we're just going to go ahead and put the analog out raw 1 right there. Okay? Because we're not even going to let them call it in any other part of the program. Now, if they try to call it in a different part of the program and we have this dragged into main, it's going to show, it's going to flip out on us, okay? So that's that analog out. That first one. No, it should be a global out. Yeah. Yep. What? No, int. The integer. Are y'all able to see that on the video? Whenever I did the videos, like the words on the boxes and stuff. Okay. All right, so I don't want um I don't want that analog out ever to get over 3.3 volts. Okay. So what we need to do is we need to figure out what 3.3 volts would be compared to 27,648, right? So let me pull this back up. All right, so if 27,648 equals 10 volts, what does 3.3 volts equal? Just imagine, right? Yeah, it's a third of whatever, 27,648. So I'll get my calculator. 9,216. Okay, so that's what our 9,216 is our mats that we're going to put out of that analog output. Okay. All right, so let's go back to our ESP32 simulator, and we're going to put that 9,216 and 0. All right, now we can normalize over here, we can normalize over here. We're going to say this is going to be, let's call this norm underscore 1. This is just a it's not garbage, but it's just a transient variable that we'll use, and then, you know, there's no sense in naming it something pertinent because we're not going to be calling that normalized number. If we ever need to know what that normalized number was, we need to give it a good name. Okay, let's go ahead and define that tag. Let's make a local temporary. Let's make it a real and define it. All right, now I want us to put it into percent. Like I want us to give a percent of what we want out, and then we'll just call it from here, right? So if I want it 45%, that's fine. We can do other scaling to get it into there, okay? So let's take it from 0.0 to 100.0. So 100% of that output. And we're going to put that norm there. All right, so you can control and drag, or you can start typing out norm. All right. And then what value is this going to be? This is going to be, we need to call it something, well, I want to test something out right now. All right, so we're going to take a reel to reel. and then a rel to int. What I want to do is I want to download this into there, and then we're going to measure on there. So I'm going to take this VFD off. I'm going to drag that ESP32 simulator in, okay? And all that ESP32 simulator should be doing is outputting a 3.3 volt signal to my first analog output, okay? We'll go back and add stuff to it, but what I want to do is make sure that's the case before we move on. That no matter what they put in there, 3.3 is the highest, okay? So I'm going to let that download into the processor, and then let's go, we'll take a voltmeter and test it. So while that's doing that, let me get a voltmeter. And let's test that we actually have.
Yeah.
All right, so I'm right at 3 volts right there. Right. So that's fine with me. Like, it probably isn't calibrated good, but 3 volts is actually fine with me because it can go lower, it just cannot go higher. Okay? All right. So I'll leave that there so we can watch it. Cool. Okay. All right. So now we don't want a hard coded 100 in there. Okay. So we need to make this variable something that makes sense to them when they're plugging away. Okay. So, and it needs to be it doesn't need to be a hard-coded variable because they might have 50 different things that they would call what they want to output to this, okay? So, let's call this simulator underscore ADC for ADAC. All right. Now right click it, define it as a local in, And it should already give you a data type of reel because it's in a spot that is expecting a reel. Okay. Now later on, we'll be able to put stuff in there and it'll convert that 0 to 100% into something, right? A 0 to 9,216. Now, what about the one that's going to go to the daughter board? We need to make, let's go ahead and drag 2 mystery boxes down here. And we're going to take norm, scale. And we're going to do the same thing for the second output, but it's not going to be scaled down to 3.3 volts. Okay. So we're going to take 0.0. 100.0. Out here, we're going to call this norm 2. All right, now if you push enter before it gets done, it's going to try to give you norm 1 again. Type it all out and then right click so you can get off of it. It's going to be a local temporary. It's going to be a data type reel. Then if you do a control drag, you can get it right there. Now this one can go all the way up to 10 volts. So we're going to put that 27,648 right there. Okay. And the output is going to be the analog out raw 2. Okay. Now for this value, let's call it analog underscore daughter. Okay. That's going to be the analog output that's going to the daughter board. We're going to define that tag as a local in so that they could hook up to that if they needed it to. And it's going to be called, it's going to be a reel. All right. So what we're doing right here is like a teacher. Let's say a different teacher was teaching this class. And you know the little simulator boards with the little switches. Imagine you had a little bit bigger one that had buttons so that you had to do cylinder circuits that had switches so you could do switches. And then it had a little microprocessor that had a screen on it that could be telling you values that you were given to it, right? And then it would also have an Ethernet jack, which wouldn't use Ethernet. It'd be a RJ45 jack. But instead of using Ethernet, it was putting out voltages and different things through those 8 lines. So you could plug a little daughter board and wire things into that, right? So you're not constantly having to wire up there and it's small enough you could take home, okay? So when they use that, they'll have to drag this box into there, and that's how they would communicate. They wouldn't directly communicate with the analog outputs. They'd have to communicate with the simulator ADAC and the analog daughter board things that we're making right here. Okay. All right. So what I'd like to do is, I want to make, well, let's drag this in there. All right, so we'll right click and we'll do an update block call. And now it's going to give us simulator ADAC analog, simulator ADAC analog daughter. Okay. Now let's put 100 in both of these spots. All right. I'm going to re-download it. Now it should stay the same for that. Now, when you download, if you see like a red no action, go and change it, and then load will come up. All right, so let's test what the voltages are off of those. So we've got right at that 3 volts. What I'm going to do is I'm going to take this second.
Good check.
Okay, so some reason our second output has been funky, but we'll figure that out in a second. Okay. That actually helps because I didn't want to send that board off and have something kind of screwy. So what's going on is that analog output isn't actually putting out 0 to 10 volts. It can put 0 to 10 volts out. It can put 0 to up to 10 volts out. But what it's doing is it's putting current out. Okay. So what I'm going to have to do is I'm going to have to put a resistor in there to convert that current into, so it's going to be a 0 to 20 milliamp current. Okay. Into the 0 to 3.3 volts that I need. Okay. So instead of doing that, you know, funky, not letting it get over 3.3 volts, right? All I'll do is I'll make a resistor network that will convert 20 milliamps into 3.3 volts. And that'll give us the full range of what we need. Okay. So what would that be? What resistor would I need right there to get 3.3 volts out? 3.3 divided by 20 milliamps, which is 0.02, something like that. So 3.3 divided by 0.02, 150. 3.3 divided by 0.02. All right, so I need a 150 ohm resistor right there. Okay, so what we'll do is, y'all remind me whenever I get done with this to add that to my circuit board, because otherwise, like, since the PLC is only outputting a 0 to 20 milliamps, we don't actually have to do this little conversion here. We're going to leave it for now, right? But the reason that's showing up right there is because it's got the right resistors. Like, you need 500 ohm resistor to get it from 20 milliamps to 10 milliamps. I mean, 20 milliamps to 10 volts. Okay. So that's what those three resistors are. There's three 1500K in parallel. So they make a 500. So knowing that that's an analog output of a current, I can change, and we could output 20 milliamps. So we'll get the full resolution of the PLC. I'll just put a resistor in line with that. Okay. So, we'll still go with that. Like, so let's go ahead and put 27,648 right here. And then on the comments for the network, we'll say 150 ohm resistor. And then on the daughter board, I'll put a 500 ohm resistor to convert that 0 to 20 milliamps to 0 to 10 volts on the daughter board. Okay. And what? 150 is 1/3 of 500, right? Just like we needed that 3.34 there. All right, what we're doing is we're just making it easier for them. They go in, they just drag that ESP32 simulator in, and it's going to have everything that they need on there. Okay? All right, now our analog inputs, both of those are coming from the ESP32. Okay? So we need to do another Normex. Need to do another Scale-Let's. That is 0 to 10 volts, but we don't want to confuse people, right? Like, the normal input for that analog input is 0 to 10 volts. Well, we're never going to get over 3.3 volts. So we want to convert that so it actually represents like the full range of it. Okay, so we're going to put 0 to, what did we have up top? 27 648 divided by 3. No.
It was 9,216.
Okay, that's right. So we're going to go from 0 to 9,216. and that's going to be our analog in volts. Okay. And then we're going to convert it to 0.0 to 100.0. I want to do it. Analog in volts. Go to your tag table and it'll be in like it'll be easier to put it in your tag table, like because you're gonna have to do an IW64. It'll be a word, right?
It's a, how about percent MD4?
IW4 or IW64. You get it?
Okay, so it's a,
Global memory is a real.
A real? No, wait. Is an integer. Analog in real raw is an integer because it's just whole numbers from 0 to 27,648. Then it should give you the option of doing IW64.
it said that it's already.
Okay, go into your PLC application tags and see what you named it in there. Okay, that's what we wanted. Like, so go back to your simulator. Oh, okay. It shouldn't be volts. I'm wrong. I'm wrong. Like I use a different tag. Like it is analog in raw 1.
You had analog in volts. Real.
Okay, okay. Yeah, I'm sorry.
Analog.
Okay, that was part of a different that was part of the analog scaling.
So you're using analog in raw.
Yeah, I'm sorry about that. All right, so we're just going to call this norm 3. Define that tag. Local temporary, a real. Command drag. Put it right there. And then we're going to make a local out called ESP underscore DAC. So That microprocessor is called ESP32. A DAC is a digital analog converter 1. All right. And it's going to be a local out. And it's going to be a reel. Okay, I don't want the 0.0 and the 92.16.0. So it's going to take it from an int to a reel. We're just going to put 0 there and 92.16. So I changed that first little box right under the norm its to an integer. Do the same thing for network 4, okay? But use analog in raw 2, norm 4, and ESP DAC 2, okay? Go ahead and put my int to real and my real to real so that automatically populates things the way it should. We'll do 0, 92.16, do norm underscore 4. So local temp. I can do a control drag over to here. We're going to convert that to 0.0 to 100.0. I could use integers there, 0 to 100. But what's the difference between 9.4 and 9.5? If I do that, then like there's no difference. If I do it with the 0.0 behind it, then just with that little bit of like 1/10 of a place, now I got 1,000 different discrete steps, right? I can get more resolute, right? Because I can tell the difference between a 9.4 and a 9.5. Where if I just do an integer, a 9.4 and a 9.5 is usually going to get what's called truncated. Instead of rounding it, everything that's 5 point something up to 5.9 is going to be a 5. Okay? Well, whatever that whole number is, it cuts the rest of it off. You could do a round, which would, double the amount of things because you'd have 9.5 and below. And then 9.51 and above, right? We're going to call this ESP underscore DAC underscore 2. And call this local out. Analog in raw 2. What this function block does is it protects our stuff. Okay, like instead of just going up to 33, like if we didn't have this normalization and scaling, it would only go up to 33%, right? And we like to think in whole big things, right? So if 3.3 volts is the max range, now we're ranging it so that like we keep everything in our mind easier, okay? Because one thing is going to be 0 to 10 volts is full range. One thing is going to be 0 to 3.3 volts is full range, okay? Remember when we did the VFD and then we changed the scale of it so that the whole of the potentiometer was changing as opposed to just ignoring everything past a certain point, right? Instead of just we get up to 3.3 volts and then everything else is dead. Now 3.3 volts is all the way to the right. You're welcome. All right. So we take, let's go back into our main. Remember to update block call every time you change it. Now, if you change it, where you have more analog in or local ins and outs, where that block has to change, you have to do an update block call. If you do code in there and it doesn't change anything out here, it doesn't need updated, okay? Okay. So before I download this, let me put that simulator ADAC analog down to 50, okay? And let's see what happens to that that needle. Mainly because what happened was I moved that number from 9,000 up to 27,000. So now it gave the full range of it, right? And then now I'm about half. So let's do 100 real quick. And then I'm going to download into there again. And let's watch the needle go down. So now,
You did 25 when it goes down to 2.
yeah. So I'm not going to get back up again. Go check it out real quick. I want to do 25. And tell me if it goes down to 2.
Yep.
All right.
Put 25 and then run simulator or
Simulator. All right, so now I can take a variable that I want to read the ESP DAC and put it there and then do anything with the code that I want it to. Cool. Nobody should get in, like we're the only ones who can get into this code block. Like I'll probably have a lesson on making code blocks, but we want to build this up a little bit more. Okay. So, no more is, like the first 4 inputs when we put the simulator on there are not switches anymore. Okay. So let's go ahead and go back into our bots, and we're going to use the most powerful bots ever. Do an MOV. All right, all MOVs do is move what's from the input to what's on the output. Okay, that is by far the most powerful bots we've got, I think. All right, so it won't let me move a bool. So let's just leave that move there for a second. How we'll move a byte or a bit is let's put a network with 4 rungs on it. Okay. I want to do it all together because these are all doing the exact same thing. Okay. All right, what do we call this? Digital in? 1. All right, do the first 4 digital in ones. I mean, digital ins. So 1, 2, 3, and 4. That should be 3. And we're going to call this button underscore 1. And it's going to be a local out. I'm going to do button 2. Local outs on all of them. Be a local out. And go up here and kill this move. I just delete it for now. Got ahead of myself. All right, what this does is it takes the regular tag table that we've got and it converts it into something that we can hook up to later, right? All right, now more than likely we'll probably kill this network also. Like, and I'll give a special tag table, like you download a tag table in a function block, and that tag table would be like for the first 4 ones, they're buttons. For the next 4, they're switches, and for the rest of them, they are outputs of the ESP32 and outputs to the daughter board, right? But for now, like I want y'all to understand the power of a function block, right? We can get this perfect, and then all of this code, we're already up to network 6, but we have a bunch of stuff in there. When we go to main, it's just taking up one thing, right? So I could put a variable here and then use it in a different part of my network. But it's explaining what it actually is. I'm going to get an analog voltage from the ESP. I'm going to get an analog voltage from the ESP. I can output an analog voltage to the ESP, and I can output an analog voltage to the daughter board, right? So by, doing the naming and being able to encapsulate all that code in a function block, like, how easy would it be just to drag this in and start coding with it, right? All right. So I want to do something in main. So let's make this analog go up and then start back over. How's that sound? All right, so every second it goes up like a volt. Okay? We need to make an oscillator. An oscillator, we got a normally closed contact. We have a timer on delay. Then we have an output. We're going to call this OSC. Let's just call it OSC2 because we already have an OSC flipping in there somewhere. It's going to be a global memory. Then we're going to use that OSC2 over here. All right, so we want this to cycle every second. So our preset time is going to be 1s. All right. So every second that OSC2 is going to pop. Now we need to drive a counter with it, right? But I don't want to use a counter. Drag a mystery box down and type in ADD. You type in ADHD, it won't know what you're talking about because it's ADD. All right, so put a normally open contact here. And it's going to be OSC2. All right, we're going to add, all right, so let's call this N1 volt underscore step. Okay? Right click it. And it's going to be a global memory. And we're going to make it of the data type real. Okay? We want to add 10 volts to that, or 10 percentage points every time we go up, right? Because we're going to be feeding something that's expecting 0 to 100. So every second, we're going to go in here and add 10% to that volt step. Cool? So as soon as that triggers every second, volt step is going to add 10 to, you're going to take volt step, add 10, and then we're going to put it back into volt step. We're just going to overwrite what it was. So every time that does, boom, steps up another 10%, right? Now, when we first do this, it's going to go up to 100, and then it's going to keep going because to it doesn't know a percent, so it doesn't know where to stop. So we want this to stop or to start back over when it hits 10. So go on the vertical bar, add a new rung, do a mystery box, and do a compare. Start putting in CMP. That's not going to work. We want it to, if it's greater than, so start typing in like a greater than symbol. Okay. So we're going to compare something. If volt step is higher than 10, then let's put another mystery box there. Move. So we're going to use that move now. And we're going to move 0.0 into volt step. Do y'all understand what this little network's doing? It's counting up. Once it gets to 10, once it goes over 10, that little network that is doing the comparison, that greater than, if volt step is over 10, then I'm going to move 0.0 back into volt step. Okay? Now I'm going to put volt step up here. And when we download this, it should. Okay. All right, let's see what's going on. Not quite. Let's see if it's a code problem. Oh,
You didn't change anything.
no, I did. What I did is I said if it goes over 10, but that's 10 volts, I need 100 right there, right? So once it gets over 100.0, since we're dealing with percentages instead of volts, all right. So that puts us in a good spot. Like, we're going to continue to do this. Like, we're going to, even before I get that board in, I'm going to build up a prototype of that board so that we can add some more stuff to this and start communicating with things that aren't normally able to communicate with the PLC directly. Okay. So we could take that laser sensor and convert that distance to, you know, whatever, and put it in here, and then control. Let's say next week I'd like to be able to take that laser sensor, and the higher we get our hand away from it, the higher the voltage goes, right? So, whoop, whoop. All right, now that seems silly, but we can do a lot of stuff with that. I mean, we could control the speed of a pump based how, you know, how far the sensor is. Like if it's way down here, turn the pump up, and then as it gets closer to where we want it to be, turn the pump down, right? With the ping pong ball? Mm-hmm. Concept. Like, have you seen that video with the ping pong ball? I can't think of where a good one is, but I've got a computer fan, I've got a clear tube, and I've got a little servo damper. And between those three things, like and a laser sensor down at the bottom, I can tell it to go this high, and then I could open up that baffle, and then like the feedback loop of the PLC would then make the fan turn up higher, so that it would compensate for all the air getting lost out of that damper, right? I'd like to, let's say this week, you got this in there, all of y'all got this in there. People outside, like I'll you know, take the analog voltmeter and let you hook it up to your PLC to see that it works. But the main thing I want you to do, like if you're watching this on video, is to build this simulator the way that we did, like the function block for the simulator. And then I want you to build that step up voltage thing on network 2 and 3 that we built, so that you can see that the voltage would be stepping up. Okay, on video, you didn't get to see that. You're gonna have to build all this, build everything in the simulator.
Cancel the network too. Does that do anything?
Nuh-uh. Or yeah, like if it's empty, if there was a red X here, you'd need to delete it. But make sure you got all this stuff in, because we're gonna build on this. We might change some of it, but we're gonna build on this so we can start interfacing a lot more stuff. All right. For your lab this week, you just did it. All right. Now next week, I'll have more circuitry. I'll probably have the computer or the camera pointed down there, and we'll be working on it more hardware based. We'll add some stuff in there, but it's not going to be a whole lot of stuff. And then we're going to do something cool with it. Do what? You can if you want to. If you want to prove that yours work, the people who are in here, you can go ahead and hook it up. Like take the Ethernet out of the wall, download it in, prove that it works. All right. If you're on video, you'll prove to me that you did it. Because you definitely need it for next week, because we're going to use this and we're going to deck it out with probably 10 more networks. All right. So let me stop streaming.